And today we talk about our place in the universe. And we spend much of the time on the question of whether or not we are alone here. So we discuss the famous Fermi problem, i.e., where is everybody? And that naturally grades into a conversation about recent events on Earth, where a renewed interest in UFOs has captured a lot of mainstream attention. We also cover the public understanding of science a bit, the impossible existence of flat earthers who still live among us, and then I try to lead Neil once again into a conversation about politics and attendant moral panics, and you can judge the results of that for yourselves. Anyway, it's always great to speak with Neil, and I hope you enjoy the conversation as much as I did. And now I bring you Neil deGrasse Tyson. I am back once again with Neil deGrasse Tyson. Neil, thanks for joining me.
Yeah, Sam. I mean, I love your show, and I never think of myself being on it, so that when I'm on it, it's like, ooh, what am I going to talk about? Because all of your guests and all of your conversations are, they anything that I do, just as a scientist and as a popularizer, you kick it up a notch and you just inject it into all of the most controversial things going on in society. And I'm just not that brave.
Okay.
So I feel like I should not be on your show. That I just feel that way sometimes.
Well, I hope not to confirm that hypothesis, but I will lead you to the edge of your courage, and you can pull me back.
Okay.
But it's great to hear your voice. But before we go all over the place here, I want to just touch upon your book, because you have a new book out, which is Cosmic Queries, Star Talk's Guide to Who We Are, How We Got Here, and Where We're Going. And let's start with the area of just pure scientific interest, and then we can go to points of controversy or not as the hour unfolds. But this is really a gorgeous book. It's published by National Geographic, so it's really well illustrated. And in reading it, I confess I have not read all of it, but I've read a lot of it, and it just struck me immediately that this is the book you would want to hand to a smart, inquisitive, science-interested teenager, or like anywhere from, 14 on up. It's just perfectly pitched to like a person's first book on science. Was that at all your intention in writing it?
It's interesting you say that, because what I learned from my very first book, which was many, many moons ago, I wrote a book and I said, well, if I'm going to write a book on science, I want to make sure everyone understands everything that's in it, right? And so my first book was a question and answer book on the universe, and I wrote it in a playful way. I had a pen name for Merlin, dear Merlin. How does the universe work? And Merlin would recall a conversation with Einstein. It was a fun, playful thing, and all the questions were asked by full-up adults. When the book came out, I found that when adults read it and they understood everything in it, they thought to themselves, well, this is clearly not for me. This is for someone younger. And I said, wow.
Yeah.
So people are accustomed to, when they encounter adults, when they encounter a science book, they expect some of it to sit above their head.
Yeah.
And so I said, oh, okay. So my next book, I'm going to have 2 chapters that's guaranteed to be above everybody's head. And no one thought about giving those to kids. But Cosmic Queries, I think, is a celebration of the deepest sources of curiosity that exist within us as humans. And all of those cylinders, if I'm allowed to use an internal combustion engine reference, all of those cylinders are firing for all of us when we were younger, right? Every day is, oh, what is that? And it's a flower and a tree and a rock and why is this and why is that? And some of those questions get very deep, like, how did it all get here? And why are we all here? And are we alone? How will it all end? And so that deeper category of question got elevated and put into this book. But the whole concept of Cosmic Queries is stoked monthly in our podcast, Star Talk. Star Talk, we interview celebrities, and I have a comedian who's a co-host. So it's very they're a force of levity on a show where content might have their own force of gravity,
Hmm.
and I dial those in so that we have a consistent product each time. But one of the more successful variants on that show is called Cosmic Queries, where our fan base just simply asks us questions, and we culled the deepest subset of those and put them into this book. So I think for me, it's a celebration of what it is to be human and be on one side of knowing something and want to cross over into another side of enlightenment.
Mm.
And yeah, it serves the curiosity in us all. I think some adults they've lost it, and so maybe it'll fan the embers and maybe ignite a flame once again, because you know it was there when you were younger. So I think I think that's why you were feeling that way about it,
Hmm.
because it makes you feel young again and wide-eyed. And thanks for noticing the National Geographic DNA in the book. It's a beautiful book. And we didn't stop at just science illustrations. There's art as well.
Yeah. Yeah.
Carefully chosen artwork that evokes the themes or the ideas in the narrative. So yeah, so thanks for calling that out.
Yeah. So is it always an exciting time in astronomy and astrophysics, or have there been periods of stagnation analogous to those in physics? I get the sense that in physics, certainly, in any given generation, there's an impressive feeling of, at least on the theory side, of spinning your wheels and not necessarily making discernible progress. But I just intuitively, it seems like it could be different in astronomy and astrophysics. Is there?
That's a perceptive point, and let me attempt to address it, whether or not I fully answer it. In physics, what you're referring to, I think, is sort of the revolution or evolution of ideas,
Hmm.
all right? And you don't get those every day. You get them maybe once in a generation, and all the years in between are filling in the gaps between those ideas. And those don't tend to get headlines, even if they're intrinsically exciting to a physicist. So in astrophysics, occasionally ideas matter deeply, yes, but what happens more frequently is that weird stuff gets discovered, right? Or interesting stuff. Water on the moon, on the craters of the moon, a black hole in the galaxy, in the center of the galaxy, photograph of the black hole in the
Mm.
center of the galaxy. I mean, so things that exist in the universe, because the universe is so vast and it has so many different kinds of objects, that in all of our catalogs, we probably missed something that is one in a million or even one in a billion. And when that gets discovered, that's headlines. And so, no, it doesn't rethink the whole field, but it is definitely fun to inventory and talk about and characterize it and try to figure it out. Now, I did do one thing. For a while, I was a postdoc at Princeton, and Princeton has our feature journal, the Astrophysical Journal, all on one wall. Okay. From its very first episode, for its very first issue, 1895, the Astrophysical Journal, up to the present. And I thought to myself, let me do this experiment. And I found the exact middle of that wall
Mm.
of all the journals. And I said, I wonder what date this is. And it was
5 years ago.
no. so so this would be sort of the halfway point. And as I did this and I kept having it, what I found is that the halfway interval of time was 18 years. It fluctuated between
Hmm.
15 and 18 years. So the total amount that was published doubled every 15. Now, not all of it is quality. You get that. I understand. But as a first pass measure of the pace of things, this was highly illuminating to me. And it said that, yeah, I mean, if you're living on the exponential curve, every day looks like you're living in special times. And I remembered going back, I have a book on the sun written by an astronomer named Charles Young. In fact, he was at Princeton in his day. I have two versions of the book. One that came out in like the 1880s, late 1880s, and another one came out in the 1890s. It was like the second edition. And like, you know, 5 years or 8 years had gone by. And you read the preface in the second edition, it said, our advances are so great in our understanding of the sun. We had to come out with another.
Mhm.
And I'm thinking, you guys have no clue
Yeah.
what a great advance is. Yet, of course, that's what it felt like when you're on an exponential growth curve.
Mm.
Everybody feels like they're living in special times.
The biggest change, and again, I have a layperson's view of advances in astronomy, really, to take the observational side of things for a moment. The biggest news in my lifetime, I think, I mean, leaving aside very sexy things like gravitational waves, is just that the fact that we crossed over from talking merely about planets in our solar system to confirming their existence elsewhere. I mean, so we lost Pluto quite famously, but we gained, I don't know how many planets at this point. How many extrasolar planets have
We're
been cataloged?
over 4,000. Yeah, and it's
Yeah.
rising fast. Yeah.
Yeah. And so, I mean, what's the safe assumption now that our own galaxy has hundreds of billions of planets? I mean, and I mean, what's the
Yeah.
number
So
you put to it?
we do that calculation, and you, in the section, are we alone in the universe? But you can ask a different set of philosophical questions, something that might titillate you. You can look at all of the layers of bias that are inherent in how we even go about answering those questions. Because even in your very statement, you said, well, how many planets? Because the life that you know and the life that I know lives on a planet.
Hmm.
But maybe life also lives on moons. Maybe it lives in atmosphere. Maybe it lives in gas clouds. So we go through all of the biases. There's a carbon bias, right? We are carbon-based life. Some of these biases I think are fully legitimate, but if you really want to search with as wide a net as possible, also consider the Goldilocks zone. So much
Yeah.
was written and talked about for decades, from the 1950s and 60s when this concept was first formulated, where we know life thrives, needs, and thrives on liquid water. So if you're going to stick a planet in a star system, not too close, it'll evaporate the water. Not too far, it will freeze the water. So there's this zone, this belt around any star where a planet would naturally have liquid water. And you need atmospheric conditions to sustain it, of course, but you're not fighting it. It would happen naturally if the conditions allowed. And so then we learned, wait a minute, the sun is not the only source of energy in town. All right. Jupiter and its tidal stresses on its surrounding moons is a source of energy. So one of Jupiter's moons, Io, is the most volcanically active place in the entire solar system because Jupiter is pumping it with energy. And so now we have to think, if life needs the warming energy of a heat of a, it just needs an energy source. Why does it have to have a star?
Hmm.
And so you just go on, and then we learn every model of the solar system that we construct, that of any star system when it's born, most of the planets that formed are on unstable orbits, and they fly out into interstellar space. It may be that there are more vagabond planets than there are planets bound to their local star systems.
Hmm.
So you say, well, that's not a good prospect for life. However, Earth still has energy sources in its core.
Yeah.
Is this how you get volcanoes and all these mid sea vents that are pumping very hot waters into the bottoms of the oceans? If you're a life form thriving on that, you don't even care if you were ever orbiting a sun. You could be a frozen lake bed on a frozen ice on top, but down below you could be doing the backstroke in your warmed hot tub.
Hmm.
So this notion that we want to look for planets and look for a habitable zone or Goldilocks zone may be needlessly restrictive as we go forward.
Hmm. So now, how have your intuitions been pushed around with respect to the prospect that we are alone versus the prospect, seemingly equally astonishing, that the galaxy and the universe is teeming with life? Have you had changes in the way you weight those probabilities over the course of your life?
Yeah, that's a great way to ask that question. I would say the probabilities have, as the as they've changed only because we learned new things, and not because I had to reevaluate what I was already thinking. I've always been very open to possibilities of the universe, just given the size and the diversity of objects and the age. Practically anything you can imagine being possible, we think is going to be possible. But there's some other really good reasons for some of the bias that we are invoking here. For example, there's a famous episode of the original Star Trek where they encounter a life form that's basically made of rock, and it moves through rock like we move through air, and it's rock-based life. And an active ingredient in a lot of minerals is silicon. So it's silicon-based life, and this was their attempt to do this in the 1960s.
Mhm.
And this was silicon-based life as opposed to carbon-based life. Well, they didn't pull silicon out of their ass, right? Why do people think of silicon-based life? If you go back to the periodic table and remember why elements form columns, the columns have similar valence electrons, which means if you're above or below another element in a table, in the periodic table, you can make similar molecules with all the same other atoms.
Mm.
Well, let's find carbon. Well, there it is at the top of the chart, number 12. What's directly below it? Silicon. So every molecule you can make with carbon, you can make with silicon. So why not create an entire parallel life system where silicon is the base instead of carbon? And so that's a perfectly legitimate chemical broadening of your bias as you go search. My rebuttal to that is you don't need to do that, because first, carbon is hugely sticky.
Mhm.
It sticks to itself and multiple bonds, and silicon also. But what you really win out is that carbon, depending on where exactly you are in the universe, is between 5 and 10 times as abundant. So carbon is already going to be at it before silicon, figures out how to put on its pants in the morning. And so I don't need to really think of life forms based on an isotope of bismuth or even silicon. So I think carbon is the way to go here, just given its diversity of chemistry that it offers us. And I don't know if I directly answered your question. Oh, have I changed any of my evaluations? Yeah.
Yep.
So the Fermi paradox is what you're dancing around there. And I want to clarify the Fermi paradox, because I think most people who invoke it don't know the full weight that it carries. All right. So you can do the thought experiment. So Enrico Fermi, the physicist, famously quipped, if there's life in the galaxy, then the galaxy ought to be teeming with life, and they would have visited us by now. Where are they? Okay. So maybe
So
they're
I
not
guess
there at all.
it might be worth spelling out why that seems so logical. I mean, just with respect to any kind of time
Yeah,
window in
yeah,
which.
exactly.
Yeah.
So you can ask yourself, well, how wide is the galaxy? So 100,000 light years. Okay. So that feels intractable. So let's say you never get to the speed of light, but let's say we get to 20% the speed of light. That means you can cross the galaxy in 500,000 years. All right. But most stars are not the diameter of the galaxy away from each other. They're much nearer. So, for example, Alpha Centauri's system from Earth, 4 light years away, 20% the speed of light, you get there in 20 years. Okay. And you can star hop. So imagine this is one of those, I forgot whose machine they got named after. You go to a planet, and then it's with a robot, and then the robot builds 2 copies of itself, and then they launch to other planets. Okay. And so, or even people or
Mm.
aliens. So they arrive on a planet, and then they say, okay, time to go to more planets. And now you go from 1 planet to 2 to 4 to 8, the star systems. It turns out if you did that, only going to 2 once you land on 1, you can, it's 2 to the n power, right? So however many years are loaded in your n, you can easily completely populate the entire galaxy in an evolutionary timescale.
Mm.
Easily.
Yeah.
And so like you can do it within a few, like, tens of millions of years. But the planet is around for billions of years. So where is everybody? That's the
Right.
question. And
And the
my
other intuition
favorite,
here, the other element to this picture is that if your complex life is ubiquitous, you would expect certain civilizations to be millions of years ahead of us. I mean, because given nearly 14 billion years to start this experiment, it would just be a miracle if all complex life were at precisely the same point in its technological evolution. So to find ourselves not surrounded by evidence of technological alien life is to suggest that it might not exist because, again, where is everybody?
yeah, and you're right. We are very Johnny come latelys in
Mm,
this. First, you have the 14 billion year old age of the universe. Then you have the 4.5 billion year old solar system. And then ask, how old is the branch of the tree of life called primates? All right. If primates were your best chance, or mammals, let's say, were your best chance of, quote, intelligence on Earth, we really didn't get underway until after the dinosaurs. And that's basically yesterday, 65 million years ago. And the Earth had been around for hundreds of millions of years, cranking out life. So imagine a planetary system that got a billion-year head start on us.
yeah,
If there's any forcing vector towards intelligence, we would be dwarfed by any such intelligence that manifested itself. And the comparison I like making, and I'll get back to Fermi in just a moment, is this comparison you always hear about the DNA between the chimp, bonobo, let's say, and a human. It's some high 90, 99, whatever
hmm
percent identical DNA. And the people who want to keep thinking humans are special will say, but what a difference that 0.5% makes. And they crowd themselves into that 0.5% and celebrate all that we are that chimps are not. But I'd rather pose the question a little differently and say, suppose the difference between humans and chimps is as small as a 0.5% DNA in the intelligence vector, whatever that vector is. Suppose it is that small. What do you say? Well, what do you mean? We have the Hubble telescope in poetry and philosophy, and they stick a twig in a hole to get termites out. And I say, well, maybe the difference between those is small. You don't want to think that way, but imagine it. So now let's imagine an alien who is 5% along that same vector beyond us that we are beyond the chimp. What would we look like to them? No reason for me to think that we wouldn't look any different to them that chimps look to us. Because a
yeah,
smart chimp can stack boxes and reach a banana. That's toddlers can do that. So what does a smart human do? Well, we can, roll Stephen Hawking forward. Here's a smart human, and they'll chuckle and say, "Oh, he derives black hole theories in his brain, just like little Timmy over here who just came home from preschool." So and that's a 0.5%. So now imagine 5%, 10%, and their simplest expression of an idea would transcend our smartest capacity to comprehend. In the same way, you walk up to a chimp and say, "What time is it?" They have no idea what your time.
mm,
You want a cup of coffee at a Starbucks? Going to catch a plane? Do you want to go to the library? None of this makes any sense to them, and they're our simplest sentences. So I think about this all the time, leaving me to wonder whether the search for intelligent life, SETI, is itself a bit of hubris
hmm
because it assumes that some other species has our intelligence and not something so far beyond us that they would take no interest in who and what we are. And one of the solutions to the Fermi paradox is that we are to the aliens what worms are to us. You don't walk down the street and a worm crawls out from the moist soil. You don't say, "Gee, I wonder what that worm is thinking. Let me go understand that." Unless you're a wormologist, no,
mm,
you're not thinking that. So one of them is that they've studied Earth and there's no sign of intelligent life to interest them. But I have my favorite explanation for the Fermi paradox. And forgive me for not remembering who to credit this to, but I don't take ownership of this idea. It's whatever drive is required for you to want to, quote, colonize planets with abandon right? You go to a planet, you have offspring, and they colonize 2 planets, and they go 2 planets. Whatever that drive is, has the seeds of its own unraveling built within it. Because what happens when the planets start becoming scarce? Your urge to do this, risking life and limb, that means it's deep in you. You need that planet. You want that planet. And so you go out, and then there's somebody else trying to claim the planet. And then you have interstellar warfare, competing over the limited
Mm.
real estate of the planets in the galaxy.
Yeah,
And then you think to yourself,
it's a
no, no, well,
version. It's a version of the great filter argument that I believe is original to Nick Bostrom. He's certainly spoken about it a lot. He might have gotten it from somebody else, but I think it's Bostrom. But I mean, the more generic idea here is that it puts most of the onus on technology. It's just once you get technically sophisticated enough, you have almost certainly built destructive technology. And, whether this is specifically weapons of war or artificial intelligence or something that gets away from you, and sufficient technical prowess to colonize the galaxy becomes self-terminating, but almost by definition. I mean, there's too many ways to kill yourself and to have all your incentives as a species not aligned that you self-extinguish.
so I would say that would be a subcategory, or maybe they're both categories of the self-destruct phenomenon
Mm,
in high intelligent creatures. Because what this specifically implicates is the same urges that infused colonial Europe,
mm-hmm,
right? So here you have Spain, Portugal, England, the Netherlands, and they all want to conquer the world. So initially they have their own territory, but then they encounter each other. And then the entire system implodes
mm,
because they can't share it, because in them they want to own it. And so this notion has already played out in this world. And that was the implosion of Europe and its colonistic ways, going from the age of the great explorers to the age of the great collapse of the colonial empires. So it's not a stretch to imagine this as sort of a fundamental truth without having to analyze the psychological profile of the alien. It's just one of these basic, simple facts that might
mm.
manifest no matter the life form.
Well, to back up for a second and to bring it back to Fermi, how has your sense of the proliferation of life or lack thereof changed once we discover things like amino acids in meteorites and in the tails of comets, which is to say that the building blocks of life seem fairly ubiquitous?
Yeah, and that's what we all find encouraging for those who are rooting for life elsewhere, because the I can encapsulate that statement in a simple fact. If you rank order the abundance of chemical elements in the universe, the number one element is hydrogen. Number two, which is chemically active. The number two is helium, which is not chemically active, but it's there. But it's a big number two. Number three is oxygen. Number four is carbon. Number five is nitrogen. Oh my gosh.
Yeah,
So
yeah, everything's on the
four out of
menu.
the five top
Yeah,
top elements
yeah.
in the freaking
And the
universe
seventh is a ham sandwich. Yeah, mm,
are contained in what we call biochemistry. And so that's why, like I said, if we were made of some exotic, like I said, a isotope of bismuth, you might have an argument to say God did something special on Earth because this stuff is not found anywhere else. But if anything, life is opportunistic. Okay.
mm,
It makes very good use of what it has. And one other fact, which is not often cited, but it has to be in the equation, is the earliest fossil evidence. It comes in of life. It comes in around 3.8 billion years ago, and Earth began 4.5, 4.6. So for the longest while, decades, people subtracted those two numbers and said, all right, life took 600 million years. That's still pretty fast. given that we're 4.5 billion years old. Okay, that's still pretty fast. It's small compared to the life expectancy of Earth, but it's even better than that. Again, I'm value judging the speed of this because the early Earth was subjected to what we call the period of heavy bombardment. There were two such periods. Heavy bombardment, Earth is still, the polite way to say it is, accreting matter from the nascent solar system. The more violent way to put it is being slammed constantly by comets and asteroids because it has a strong gravity in its region. It's clearing out its orbit, and all that material ends up going somewhere and it lands back on Earth. And so the Earth is gaining mass, and by gaining mass, it gains even more gravity. It becomes even better at it. And over that time, Earth's surface is sufficiently pelted that the temperatures prevent the formation of complex molecules. Because under high temperatures, the molecular bonds break.
Hmm.
And every time you try to experiment with it, it gets broken apart. So it's not conducive to the experimentations of life. So if you're going to start the clock, wait until the period of heavy bombardment is over. That's like 4 billion years ago, not 4.6. So now you start the clock. Now Earth has some chance of cooling down and making complex molecules and starting the birth of biochemistry. And there it is. Earth went from organic molecules to self-replicating life within between 1 and 200 million years in the early universe, in the early Earth. And that's stupefying.
Yeah.
So if it did it that fast using native ingredients on a planet just formed like any other planet, then no one who studied this problem is walking around saying we're alone in the universe.
Although there is the additional improbability, whatever it is, of getting from life, single cell and I guess multicellular, to technologically advanced civilization. I mean, you can argue that we have barely accomplished it, and there's really no sign, but for us, there's no sign of natural selection producing anything like civilization without us. So again, we're sampling this in a very narrow time window, and who knows what the next million years might bring. But I guess let me just sharpen up the Fermi intuition here. If you had to bet or assign a probability to one of two outcomes, or one or two states of affairs, one, we're alone with respect to complex life or technological sentient civilization built-in life. So there might be microbes elsewhere in the galaxy, but there's nothing like us pining for other star systems, versus the galaxy was or is teeming with advanced life, and for whatever reason we don't see it. Which seems less astonishing to you or less unlikely?
Yeah, I have to think about it the way you worded it, but it's because I don't entirely agree with what part of your premise.
Hmm.
So look at beavers. Beavers are mammals. They have large brain, like relative to other branches on the tree of life, and they fully exploit the resources in their environment. Oh, there's a tree. I'm going to use that tree to dam this river, and I'm going to make an underground den. All right.
Yeah.
Are we any different from that? We use trees. Well, first we use grass to make huts. That was available. Then we use trees. That's pretty convenient. Then we found metal. Oh my gosh, let's use that. Okay. And then we learned how to make alloys. Let's do that. And then we learned chemistry. Let's do that. So yes, it takes thresholds of intelligence to exploit your environment even more. But the simple act of exploiting an environment is not unique to being human. That's
Yeah.
my first point.
Yeah.
Second, the Romans were no less smart than anyone who followed them. All right. Smart in terms of what their brain could figure out. But they didn't have alien communication technologies. They didn't have radio telescopes. They didn't go into space. So imagine the Roman Empire and aliens are waiting for a return
Mm.
signal back through space and
Yeah.
no return signal. So
Well,
they'll say there's no.
they're still trying to do arithmetic with their Roman numerals. That was the that was the problem.
Yeah, they needed the Arabic numerals for
Yeah,
that one. Yeah, but people forget that Roman numerals do not have a zero.
yeah.
You cannot represent a zero with Roman numerals, and that's why the the calendar, the Christian calendar, Gregorian calendar, and the Julian calendar, there's no year zero. It went from 1 BC to AD 1,
Mm.
and because no one could wrap their head around it. So yeah, arithmetic is hard with Roman. I think they would have figured something out. I think they were smart folks
In the
back then.
fullness of time. Yeah, no, I mean, I take your point, and we should be humbled by how much change can occur over vast timescales, right? I mean, you look at the rest of what's on Earth with us now, and it's hard to imagine anything evolving into the kind of species that could do more than we're managing to do. But we're just looking at asynchronous lines of evolution, right? And given
Yeah,
millions of years, basically everything is potentially available.
and millions is short compared with billions, right?
Yeah.
A billion is 1,000 times longer than a million. And here we were, some kind of fist size or smaller shrew or some kind of rodent running underfoot, trying to avoid becoming hors d'oeuvres for T Rex. And that's how it would have stayed if the dinosaurs didn't just get unlucky and an asteroid takes them out, pries open the niche, an ecological niche that allows mammals to evolve into something more ambitious than a rodent. Meanwhile, rodents are still among us. So I want to impress upon people, if they didn't otherwise sort of wrap their head around it, that we went from rodents to humans in 65 million years, and that's a vanishingly small fraction of a billion years, and Earth has been around for 4 billion years. So now here's the tricky part. If you line up, this is a little thought experiment. If you just lay Earth's timeline out on the wall, left to right, beginning to end, and then you blindfold yourself, like pin the tail on the donkey, and then you walk up to it. You don't know where you are, and you pin the tail. Most of the places on that timeline you pin it, Earth only had single-celled life. Complex life was relatively late, last half a billion years.
Mm.
And then what we call intelligent life and big brain mammals, even smaller than that. The point is, if Earth is any indication, if it ever gets to that, then it's fast. So
Mm.
imagine it got to that sooner. Or the other side, flip side of that is imagine the asteroid never came. There'd still be dinosaurs here today. You know how I know that? Because dinosaurs were around as a community for 300 million years before the asteroid. So what's
Mm.
another 65 on top of the 300? They'd still be here. So
Mm.
what this tells us is what we think of as intelligence clearly is not important for survival. Otherwise, roaches would have really big brains, right? So maybe the big mistake here is thinking that intelligence is an inevitable consequence of evolution, when all it would have taken was one broken branch. Then that could have taken out all the mammals from the vertebrate chain, and then we would not have anything like we think of today as intelligent creatures.
Yeah, but if you run this experiment billions upon billions of times, it's
Well, there
just
you go. That's the answer.
as long as we have on the assumption that we're by in no way unique, and we being species of Earth, and if multicellular life is ubiquitous in the galaxy or in the universe, and you just have those hundreds of billions, ultimately trillions of similar experiments to run, then it's very difficult to imagine that you don't have, at minimum, tens of millions of cases of advanced technological life.
That's how you get to win the argument in the
Yeah,
end. You say, "Oh, what are the chances of that happening? 1 in a million?" Okay, 1 in a
yeah,
million, and there's 100 billion star systems out there. So run the numbers.
yeah,
No one is thinking we're alone out there.
yeah. But is that actually the opinion in the field? If you polled people at a conference of physicists and astrophysicists and astronomers, you think a large majority would say that advanced life is ubiquitous in the universe?
I think the only sensible way to do it is to just we have a sample of one. So let's just start with that and ask what fraction of the total timeline of Earth has Earth had what we would call intelligent life or big brained life?
Yeah.
And what fraction of that period has it had intelligent, the Drake equation? And what fraction of that period has intelligent life with technology? So if you do that, then that gives you a set of fractions that you can layer onto the entire stellar population of the galaxy. And even using highly conservative estimates, you do not come out with us being the only life form around. And like I said, if you look at the actual map of the galaxy where we have found these 4,000 exoplanets, it's this tiny little circle around. The star has to be close enough to get good data to know whether it has another planet around it.
Mm.
And you say to yourself, gosh, this is what leads to that analogy that comes from the SETI Institute with Jill Tarter and Seth Shostak, where they say, if you're going to say, well, how could have we found life? We haven't found life yet. And that's like taking a cup, an empty a glass, and scooping it into the ocean and pulling it out and saying, the ocean has no whales from this tiny sample of the vast ocean that you know you have yet to search.
Yeah. But what do you think the limit is on getting a truly optical look at an exoplanet? I mean, any of these large telescopes that you describe in your book coming online, how close are we to seeing anything of interest in another solar system?
Yeah, that's a great question. So you can ask, let's ask it another way. If you're on the moon, how well can you see sort of cities on Earth? Not very well. Those images you see on the screensavers where you have the space station orbiting, they've pumped up the brightness of those cities so they can stand out as beautifully as they do.
Mm.
But if you're going to go 250,000 miles away from them and stand on the moon, you become much less visible. And that's our nearest neighbor in space. And allow me to quantify this. Imagine a schoolroom globe. And I'm always sad because there's always color coded. And so you think of Earth as a place divided by countries, not unified by land and water and atmosphere. That's just me getting sentimentally cosmic on it.
Mm.
But you can ask, well, at what altitude above that globe would you find the International Space Station? Half the people I've asked that come away about a foot from it. It's about no, it's 3/8 of an inch
Mm-hmm.
above the surface. All right, now where would the moon be? Well, we're so jaded by how often we see the Earth and moon drawn in a textbook, people tend to put the moon maybe a foot or two away. No, the moon is 30 feet away. Where would Mars be? A mile away. Space is vast. So to directly image a planet, yes, that could be on our horizon, but to image it in a way where we're going to see roads and cities, I think that's unrealistic. But I say that, but smiling because I know what we're already up to. All right. You want to see life forms waving back at you. What I want to see is any evidence in the atmosphere that anybody's alive on that planet's surface.
Yeah.
And these are, we call them collectively biomarkers. Right. So so I didn't know this. I had to figure this out. One of these, my own, that I gleaned as I got older and wiser and learned. And so you grow up and you see these science fiction stories, and take Star Trek again, for example. They never donned spacesuits. Right? You
Mm.
ever wonder
Mm.
about that? They never,
I,
never.
I,
They're
I,
walking around on all kinds of planets,
yeah.
no space. Okay,
I
why?
also wonder
Because
about the suits they were wearing, but that's another matter. Yeah.
that's the
Yeah.
60s. You were too young.
Yeah.
Okay, I remember. All right. So I get to pull rank on you with my age
Yeah.
here. So they never wear spacesuits. Why? Because they have sensors. And they say, Captain, it's an oxygen nitrogen atmosphere. Okay, let's go down. As though if you searched enough, you would just simply find oxygen nitrogen atmospheres. What I didn't know at the time, and I don't think they knew either, is that we only have oxygen because we have life.
Right.
That's the only reason. And not only because we have life, the life is constantly making oxygen because oxygen chemically is highly reactive. So if you start out with a planet that's born with oxygen, it'll go away. It is going to react with all manner of things and it'll go to zero in very little time. So the fact that we have an active fraction, 20, 21% air of oxygen, tells you something is constantly making it, and that's the photosynthesis in plant life. So if you find a planet that has a stable supply of oxygen, oh my gosh, bump that to the top of the list. And there are other unstable molecules like methane, although there are other ways you can make methane. But the people who are in the business of studying the chemistry of atmospheres, they've got a laundry list of of molecules that will be the product of all kinds of life that we know goes on here on Earth. And one of them was
Right.
phosphine. You may remember the news stories. They found phosphine in the atmosphere of Venus, where it's not so hot, scalding hot on the surface. You come up a little, it's a little cooler. Phosphine, no one can figure out how you make phosphine other than by the natural chemistry of life itself. So that got it, that made headlines. It's been questioned for other
Mm.
reasons since then. But so we have this cottage industry of people studying the atmospheres of exoplanets now that we have the catalogs of exoplanets ready for our perusal. And I think that's where the answers are going to come.
Mm.
And one last point about that is I joke that if you find a planet that has hydrocarbons in their atmosphere, but also smog and soot and other things, that would be the sure sign of the no intelligent life at
Mm.
all. It
Uh,
is
yes.
polluting its own air. And
Look in the
one last thing I'll
mirror.
tell you
Yeah.
about the atmosphere is the thickness of our atmosphere is to Earth as the skin of an apple is to an apple.
Right.
So we think of this as this huge ocean above us when it's not, and it's actually quite fragile.
So this connects rather nicely to recent news stories about the aliens in our midst. And I got to imagine you were hit with all manner of communication of human origin about this behind the scenes, because even I was, and
Mhm.
this is not my wheelhouse. But so what we've had, we're recording this in just edging into the second week of June. And so we've had recent disclosures in the press that the Pentagon and the Office of Naval Intelligence primarily have thrown up their hands and have admitted that we are in the presence of technology that they can't explain. And they've put forward some classified evidence, apparently, that is supposedly better than the stuff that has leaked out. And the media has seized upon this. There have been really prominent stories that were not at all skeptical and not marshaling any of the legacy of skeptical debunkings of this kind of material in their reporting. And so we have 60 Minutes and the Washington Post and the New Yorker, the New York Times. I mean, really more or less everyone in sight has given a very fair and one might even say credulous hearing to these reports. To my eye, it's just not really clear what's going on. I've said this on someone else's podcast, on Lex Friedman's podcast, that I had received a sort of an advanced communication, advanced with respect to the calendar, not with the details, that this was coming. And I was urged to sort of prepare my brain to receive these startling disclosures so that I could help shape a public conversation about this new consensus, which purported to be, again, it seems to me the shoe really never quite dropped, and I want to get your opinion on this. But what I was asked to anticipate was that the people who are best placed to assess the evidence, the people who have the radar evidence, the Navy pilots who have the dash cam video, the analysts who have pored over these data for now several decades, they have formed a consensus that there's no way what they're seeing is a mere artifact of glitches in our technology. It does not admit of any truly skeptical interpretation. No, we are in the presence of technology that is so advanced that it could not be of human origin, and we don't know what to make of that fact.